Hello and welcome to this first case study in this introductory section in this course, Winning Prototype and Product Development. So let's take a look at this case study of developing a winning prototype and product in the first attempt. So almost impossible thing, we're trying to attempt it ourselves. So this is an ultra focused case study of one prototype, no second chance. And the whole story here, whole case is all about developing the prototype and getting it right the very first time. We're not going to talk about branding, marketing, scale up, distractions. So this is ideal for engineering, design, innovation, and development training, right? So that's what we're going to talk about. One prototype, no second chance, only prototype. So what is the situation? So it's all about Karan, a masked, face masked person, 28 years old, a mechanical engineer at a small manufacturing firm, who's been tasked with developing a new foot operated water pump for the rural households. But there are very not negotiable realities that are facing him. And what are these? Only one mold tool approval is allowed, right? He'll be able to build only one tool, one mold, right? So he cannot fool around with having multiple molds. And there's no budget for multi-cycle prototyping. He has to get it right the first time. And if the tool fails, the project is cancelled. It's that serious. And 40,000 units will be built directly from this prototype design. And his manager says that your prototype is your final product. There's no safety net. So that's a true first attempt prototype constraint in this situation for current, right? So what exactly is the challenge here? The challenge is how do you design a physical prototype that will behave correctly across thousands of units, locations, and usage style on the first attempt? Because errors in prototyping stage happen, and they happen through geometrical flaws that are replicated 40,000 times, that will be replicated 40,000 times, weak link failures at national scale, you know, permanent tooling loss, and immediate market rejections. So these were the many challenges that Karan was facing. So how do you design? Let's take a look at what did he do. So first is tried and understood why first prototype failed, right? And he studied and understood and came to conclusion that the mistakes in prototyping happen because we design for one use at a time, and it becomes fatal because real world diversity breaks it. Second mistake we do, we test it in clean environments, and it fails because the field conditions destroy it. They are not clean. Then we test it, the prototypes we make it is for lab loads only. And real abuse is much harsher, and that's why it becomes fatal for the prototype. Then we do design the sharp tolerances, right, in the lab scale, and it becomes that kills it in the manufacturing because manufacturing variations don't allow for sharp tolerances. And the last thing that he figured out was that it's a designer only testing in this prototyping, and user behavior is completely ignored. And that is some of the reasons he could understand why prototypes fail. And once he learned that, he decided to use what is called a zero iteration prototype engineering discipline. Now, what that is, let's take a look at that. So, the zero iteration prototype engineering discipline isn't a single formalized field, but rather a concept pushing for near instantaneous design, test, refined cycles using advanced simulations like EDAS, AI, and seamless digital physical integration, aiming to achieve zero iteration time, where feedback loops collapse, allowing engineers to fail fast, fix instantly, and evolve designs without waiting for physical builds, moving beyond traditional slow physical prototyping to rapid digital evolution and faster delivery. So that's what he decided to use, zero iteration prototype engineering discipline. Now let's see what did he do. So he built this five-step model, which he called the first attempt prototype protection perfection. Let's take a look at what did he do. So first step, what he did was he locked the prototyping problem before doing even any sketching. So, instead of saying I will design a pump, he defined the required outputs in terms of what will the product specifications be, what is that customers want, which in turn the product should deliver. Before he got into any product process or process control design using QFD process, quality function deployment. If you're interested more, obviously you will see this in the case in the course as you go along. And these outputs were like 20 liters per minute of output, continuous usage for 15 minutes, negligible leakage, withstanding muddy water, and operable by a 12-year-old or a 65-year-old. And this becomes the product specification or prototype performance contract. This is what prototype must deliver. So that's how he locked the prototype problem. Then he got into, thinking about the failures first before even designing. So with some rough design in his idea, he used FMEA, failure mode effect analysis, where he, instead of asking how should the prototype work, he asked how is it most likely to fail? And he designed explicitly for seal breakdowns that he figured out were the frequently and likely things to happen, liver fatigue, backflow jamming, sand ingestion, misaligned stock. So he figured out, he anticipated, brainstormed what are the possible failure modes and how they can affect and what should he do at this stage in designing. And the prototype was built around resisting these failures, not just delivering the output. So second step was failure first design, not function first. The third step he did was he did extreme condition prototype testing before tooling. He simulated, 10,000 stroke cycles, drop testing, tilt misuse, overpressure, mud plus sand contamination, and he intentionally allowed children to misuse it, elders to force it, and users to operate it out of the rhythm. Only after surviving abuses like this does the design move forward. So that was the third step that Karan did. Then he in designing he looked at design for manufacturing or tolerance for mass manufacturing engineering. He deliberately loosened non-critical tolerances, added self-aligning joints, introduced symmetrical parts, and eliminated exact fit dependency in discussion with the production team. And this ensured manufacturing inconsistencies did not become a failure. So that was the fourth step. And finally, he made a single shot tooling decision gate. So before approving tooling, he said that the design must pass 8 irreversible checks. And what were these? First was repetitive fatigue endurance. The design must be able to endure the fatigue again and again. Also must be able to tolerate field contamination. Also survive the user misuse, must be able to tolerate thermal expansion, also immunity from assembly errors in production, and transport damage resistance should be able to resist any damage in the transport and material aging as well, and also survive the maintenance neglect. So only when the mold met these decisions, the design met these tooling decision gates, 8 of them, was the mold approved. So that was the step 5. So what was the final outcome? So, once he designed this prototype with this kind of approach, 40,000 units were produced directly from the first prototype design. Failure rate after 6 months was 0.9%, quite significantly good, though could be better. Zero catastrophic breakdowns, there were no major breakdowns, and product adopted by multiple villages and design licensed internationally. And the factory manager said, this is the first time we have trusted a first prototype and it hasn't betrayed us at all. So that was the final outcome. So what is this insight to develop a core prototype? A first attempt prototype must be engineered to work once, must not be engineered to work once, but to fail safely 1,000 times. So focus should be on avoiding failures. And if you avoid all possible failures, won't it work? right? So that's a core prototyping insight if you want to do it right the first time. So let's take a look at this first attempt prototype mastery checklist that Karan used. It started with the prototype committing to numerical performance, the outputs, the QFD product specification. Failure modes were mapped using FMEA before designing, which define what are the kind of failures can happen with design and what should design take care of. Then it took care of abuse of material testing, that control the testing, abuse testing continued to beat the control testing, so it was tested in severe conditions. Then tolerance cushions replace precision pride. You need to give tolerances, and tooling is the real point of no return. So you need to be very careful about approving the tooling. And the real test user is not an engineer. That's a checklist. And only one perfect prototype beats five pretty ones. So that's the first attempt prototype mastery checklist that you can also use if you are an engineer. So what do we do in the next module? So in the next module, we get on with understanding what is a winning prototype. We have defined it. We will bring in some amount of marketing concepts so that the prototype that you get developed not only gets accepted within the team, but also by the customers. So what that winning prototype is, that's what we will define and then get on to discussing how can you develop such a prototype using some of the principles we have already talked about. So thank you so much for watching this introductory case study in this course, Winning Prototype and Product Development. I hope you're beginning to learn new things, beginning to enjoy, and I do look forward to see you again in the next lecture. Please feel free to message me if you have any questions. I'll be happy to answer your questions, and do download the PDF file to take a look at anything that you need to.